Hey, we're going to go through and show why we have different amounts of sunlight in the summer versus the winter, and also why there's different seasons. So that's kind of the point of where we're going. So I have my sun here in the middle, and I have my Earth here, and this purple is supposed to be the Earth's orbit around the sun. And I should mention, first of all, this is horribly, terribly not to scale. The sun is way bigger than the Earth. The sun is way further away from the Earth, and so on and so forth. But we have this blue Earth. We're going to take and move it around the sun. So right now we have here, if it takes us 1 year to get all the way around the sun, divide that baby by 4, that means that we'll be a quarter of the way around the sun. We will be right here 3 months later. Give it another 3 months. Our Earth is kind of tooling around this way. Another 3 months, we're going to be up here. And then another 3 months later, zoop, we're going to be over here. So once around the Earth gives us a year, so we're going to have different seasons. So if we say right here is fall, 3 months later then we would be in winter. 3 months after that, we're back to spring. And 3 months after that, we're in summer. And we go through these 4 seasons as we go around the sun. So the first foray into how we get daytime and nighttime is, well, this sunlight's going out in all different directions. So it's going to be going out like so. And when the sun hits the Earth, that's going to light up the Earth, and we call that daytime. So this side of the Earth here, then, is going to have sunlight on it. So we'd have day and we'd have night. Now, our Earth is spinning around in its orbit, so the spin here gives us each day. So a day, and so on as it's going around. So we'd have daytime, then is that point in the Earth, oh, sunset, now it's nighttime, and then, oops, sunrise, I can start seeing the sun, and then noon, and so on. And we get that same thing for each of these points kind of going around the sun. That day is going to be right there, day is going to be right here. So day is always going to be on the part of the Earth that is facing the sun as our blue Earth is spinning around in its orbit around the sun. So we're going to look at how Earth is oriented in order to give us, those differing, so we kind of looked here at like day and night, but how can we have different amounts of day and night as we go around? So I'm going to first here on the left, I'm going to say this is going to be summer, and maybe I should say in the northern hemisphere, so looking at the top of the Earth, because when it's summer here in North America, down in South America, it's going to be winter. And I'm going to do over here a winter, and that's going to be in the northern hemisphere. So if you look at this screen as though it's flat kind of on a table, I want to kind of try to take and get it so our eyeballs are down like here. So we're kind of like here, and we're looking like straight at this thing. So it's like we're going to hit this, and then like right behind it's going to be our sun, and right behind us the other thing. So we're kind of looking down at this thing on the level. And that's how my next drawing is going to be situated. And that's how we're going to try to do these things here. So when we draw our Earth, if you can picture a globe in a classroom, so I have my round blue Earth here, and if you can picture a globe in a classroom, it's not it's not straight up and down. You know that if this would be, this pinkish here would be like the axis, and the axis goes through the Earth. So the Earth is tilted over on the sides. We'd have like the North Pole down here, we'd have the South Pole down there at the bottom. I'm a little bit out of space, so South Pole's down here at the bottom. And I'm going to try to delete or get rid of that stuff in the middle. Oh, I can't get rid of the stuff in the middle, but I could color it blue. So I got that kind of out of there. And now the equator then, if our Earth is tilted, the equator should be a black line that runs kind of down through the middle. So it's going to look something like, the equator is about halfway down, so there and there. But because our Earth is rounded, it actually looks like it's a tiny bit curved to try to make this look a little bit like more three-dimensional rather than 2D. So we have there our Earth. And our Earth now is tilted 23.5 degrees. Let me grab a different color here. If we would have straight up and down would be something like this and this here. So you'll notice now that our Earth is rotated over to the side 23.5 degrees. So that's going to be the tilt there on the Earth. So I tried to delete off that vertical line. You can kind of see it a little bit if you look at it, but in the winter time I made this copy over here. The Earth actually has that same tilt in the winter time. So here in the summer we have this tilt here, 23.5 degrees. 6 months later, over in wintertime, we still have the same tilt. And actually, in fall and spring, we could draw the same Earth, and we'd have that same tilt. And that's because the North Pole is pointed towards this star. That the Earth's orbit, or the tilt, stays the same as it goes around the Earth. And if we would zoom way out, and I probably should be zoomed out even further than what I am here, because these two lines are essentially going to be parallel, and it goes to a star that we call Polaris. If you're kind of a stargazer at night, you'll notice you have your Big Dipper and your Little Dipper in the summer. And the Big Dipper has like stars kind of like here, and then the handle kind of goes off. If you take those two ends of the Big Dipper, they go and line up right with Polaris, which is at the end of the handle of the Little Dipper. So anyways, that's our Polaris, that's the North Star. Both of these should go in a straight line to Polaris. So as our Earth goes around the sun, the tilt stays the same as that thing moves around. This might be a little bit dangerous, but basically saying like, yep, there's that. And then 6 months later, we're here. 3 months later, 3 months later, 3 months later, that the Earth kind of keeps that same orientation as it orbits around the sun. Okay, we can zoom back into kind of what we're talking about down here. Now this is where the things not being to scale is going to totally mess us up. Because we talked before about how the sun is ginormous compared to the Earth. So the sun's going to be this huge thing shining at the Earth. It's way taller than the Earth. But now I need to delete all this to get that out of there. So what that means, though, is that these light rays, as they come towards the Earth, are coming essentially parallel towards the Earth. No need for you to watch me draw all that. I paused it, quick drew in the sun. So the sun is ginormous. These light rays are coming parallel, and they're hitting the Earth in our summer diagram over here and in our winter diagram over on this side. So what happens then is, kind of to reiterate what we drew up here, that side of the Earth that's facing the sun is going to be lit up. So I'm going to have this here and highlight one side. And same thing over on this side here, that half the Earth is going to be lit up. So you'll see now that I have this side of the Earth lit up, and you have to kind of picture this as being three-dimensional. So it's this part here kind of curving around the front till you get to this edge, and then it's going to be curving around the back till it gets halfway across the back as well. And same thing over here. This side here is going to be lit up because that's the side facing the sun. That kind of mirrors our drawings here and here. So if you picture a point on the Earth, so if you look at, say, where we are, we're about 43 degrees north of the equator. So 90 degrees would be up here at the North Pole, 0 degrees is at the equator. So we're going to be almost halfway. So now as we orbit around, our Earth is spinning, so we kind of do this loop thing here as it rotates. So it's dark. Ooh, sunrise, so the sun's just peeking around the corner. Now we have daylight overhead, and it's noon. Then we kind of curve around the backside. We're still in that lit up portion. And now we have sunset, and then we go into like where it's dark over here, come back around, and now sunrise again. So we have that sort of rotation going on. And the same sort of thing here, that when some part of the Earth, so maybe pick at the equator then, the backside of the equator comes around, it's light right now, so you have the sunrise here, and then they're coming around, oh, now the sun's directly overhead, it'd be like noon-ish, and then, or afternoon, and then you have the sun kind of going down and setting, and once you're moving out of the sun, that'd be sunset, and now you're traveling through your nighttime, and so on. So if we're looking at latitude, we have 0 degrees here at the equator, 90 degrees up at the pole. In Grand Rapids, we're rocking about 43 degrees. We're just under 43 degrees, so we're a tiny bit less than halfway. So we could be like right about here height-wise. And if that's the case, then our path around the sun is going to be something like this here. And we curve around the back side of the moon, or backside, that's a Pink Floyd album, Dark Side of the Moon. So our path is going to be something like that green kind of circle there. And it looks like this goes high. I'm really just trying to show that that's in this back part of the Earth. So for us in the summer, when we're tilted towards the sun, our path is going to be something like this as our Earth spins around. And make my arrow a little bit better there. So if we look at the summertime, we have, so we're coming around, it's nighttime, we're in the dark, and boom, sunrise. Oh, it's gorgeous. Okay, now it keeps going. The sun is going to be directly overhead. Now it's afternoon, it's getting late, we have supper, we play with our friends, and okay, about 10 o'clock, way late at night, sun sets, and we have this dark time. So if you look for us, we have this huge amount of time in the sunlight during the summer, and we have this small amount of time in the dark in the winter. And it's actually going to be about 8 hours of dark and close to 16 hours of sunlight at the absolute peak. And what we do is we call that peak going to be the summer solstice. Um, if I look at, well, what's happening to people that are up near the Arctic Circle, so up near Alaska, let me find a different color that I like better. All right, so someone will say up near here, this is our North Pole right there at the top. Pick someone that's up near the top. So now for them, they're going to be doing this path here, coming around, then kind of like going around the back side, and then coming up through this way. So if you notice, that whole circle there is all inside the sunlit part. So if you go far enough north, like up into like Alaska, Yukon Territory, something like that, you get it where it's light the whole time. When I took a mountaineering class up in Alaska back before I had kids, went up there, we flew into Anchorage, got there after midnight, and then took a taxi to a bed and breakfast. Stayed at this bed and breakfast up near Anchorage, and got in there. It's 2 in the morning, 2:30 in the morning. I remember sitting up in bed inside the house, like with just a normal window, and I could read a book. I couldn't fall asleep. I could read a book without a light, just because the whole thing, 2:30 in the morning, we're back here, but it's still in that daylight part. Similar thing, but opposite's going to happen down here. If you're south of the equator, you're going to be following a path around, and you're going to have lots and lots of dark. All of this part's dark. You have this little bit of light time. But we could look at winter over here on this side. If we switch back to green and look at us here, we're going to be a little bit less than halfway up, something perhaps like this. And we're going to be in the daylight over here because we're facing the sun, so right and left are kind of flipped. And then the rest of our path is here. We cut around the corner and kind of do the back side, something like that around the back. So now in winter time, have it where sun, well, actually, wrong thing. Winter time, you get up for school here and it's dark. You get ready, you come to school, and then, hey, the sun comes up. So then as the Earth's spinning around, you travel around here. Sun's directly overhead. It's actually quite low on the horizon, but it's above you. And then we come back here, school's out, and then about 4:30 the sun sets, and then you go and you have supper, and it's all this dark. So winter time, here at our about 43 degrees, a little less than 43 degrees, you have a little bit of time in the daylight, and you have longer at night. So this is kind of the two extremes. I'm going to import a picture a second. So jumping back up to this top picture before I show you the other one that I had, that when we get to the point where our Earth is tilted as far as possible relative to the sun, so we have the tilt here, we're tilted mostly towards the sun, they call that the summer solstice. And that is going to be, I don't know, beginning of summer, like June. Okay, winter solstice is going to be, I think it's December 23. This here's the winter solstice. And that's going to be the shortest day of the year. And then when we have the fall and the spring is going to be when it's tilted kind of compared to the path, like not towards, not away from the sun. Those are called equinoxes. So it's the fall, or they call it the autumnal equinox. And the spring is going to be the vernal equinox. And that's because, I'm not going to mess up my picture too much, but if you picture the sun, say that spring one, if the spring one, it's pointed on an angle here, kind of like this one up here is. So the sun would be like where we are, looking directly at this picture. So it's going to light up this whole side. So it's equal. You get an equal amount of sunlight below the equator as you do above the equator. So they call it an equinox for that equal. That's the beginning of fall and the beginning of spring. Okay, so now that we have those defined, we can go down to this picture that I slurped from the book, looking at the length of the days. So you see at the summer solstice, when we're pointed mostly towards the sun, for us, we're kind of in between here. We're about 43 degrees. So we do have between 15 and 16 hours of sunlight. So we're real close to 16 hours of sunlight. And then if it's 16 hours of sunlight, we'd have 8 hours of dark. The winter solstice, that other one on the right that we looked at, well, then we're going to have between, say, 8 and 9 hours, so 8.5 hours maybe of sunlight. And then we have 16 hours of dark. And look up at the North Pole. Well, North Pole, or close to the North Pole, up above 70 degrees, you're getting 24 hours of sunlight for that one day of the year, and probably some days on either side of it. Winter solstice, you're getting 0 hours of sunlight. I didn't actually do that winter one, did I? So if we're looking back here at our winter one, if you have somebody up near the North Pole, so you have somebody here, well, as they're going around, they're going to be in this dark spot the whole time. If they don't poke their heads out into this light part, then they don't get light. And now the opposite's going to be true, kind of like I mentioned at the beginning, that you get opposite seasons on the other side of the equator. Well, if winter solstice here, we have all winter in the northern hemisphere, we have all dark, while somebody down here near the South Pole, in the Falkland Islands perhaps, is going to have like all light. And that would be their summer in that other hemisphere. All right, the last thing I want to cover is the seasons, and how come we have different seasons. And we're going to look at this kind of a couple different ways, and we're going to use these drawings that we already have. So I extended out those sunlight lines, and here's the first way to look at it. And I'm not as big of a fan of that, to be completely honest, but I tried doing a fairly equal concentration of the sunlight here. And so the light rays are coming out parallel, because remember the sun is ginormous compared to the earth and really, really, really far away, so those two things make them come in parallel. So if we look at half of the earth is below the equator, half of the earth is above the equator. Well, in summertime for us here in the northern hemisphere, if we look at, well, how much sunlight's hitting the earth, and I have 1, 2, 3, 4, 5, or at least 4 light rays that are hitting, the equator or above. So this half of the earth then has this concentration of 4 of the sunlight. Down here only has 2 for hitting the whole thing. And I actually had to redraw this bottom one just to make it hit the thing. So if our northern hemisphere has 4 sunlight, this has 2. This really has twice as much sunlight. So if you have twice as much energy from the sun, it's going to make things warmer. If you take and do that similar sort of thing here in the winter time, well, for the northern hemisphere in the winter, we have these 2 beams of sunlight that we're kind of sharing over this top half of the earth. Down below, I have 1, 2, 3, 4, 5. Well, this one kind of misses, and this is kind of in the middle. So say you have 4 that hit down here below. So if I have 2 on this half, 4 on this half, you're only going to have half of the sun's energy here that the bottom part does. So if you have half the energy, it's not going to be as warm. It's going to be colder here in the northern hemisphere. So that's one way to look at it, as though that in the summer you have more energy per square foot. And you get the same sort of thing, really, in the second argument. And I think the second argument's better. I kind of look at that first one kind of like the JV. So you'll remember the JV versus the varsity argument. So you'll remember that this here is going to be our summertime. So we're looking at the summer. And in a perfect world, these lines would be more evenly spaced. And unfortunately, they are not. But I'm going to pick another bright color a second. And we said that we are right about here. So let's look at us in the summer. So in the summertime, if I have these things spread out, we're taking this sunlight and we're spreading it over this much of the Earth's surface. So this much energy then is coming at us right here. And you have to remember, it's not just vertically or along this way, but it's also going left and right. That we're really looking at kind of spreading out in like a box sort of shape or a round sort of shape. And I'm going to try to erase those off of there a second. But we have that much energy. Well, in the summertime, if you go south closer to the equator, we should have that those next 2 beams of light, that are evenly spaced, would be something like this. But that hopefully this thing here looks a little bit shorter, and it's a tiny bit. I think my lines are a little further apart down here. But if it's over a smaller area, then you're going to have it more intense or hotter. And if you go down to Alabama, Missouri, something like that in the summer, it's hot. Where as opposed to you go up closer like the UP, you go up further north, well now this thing here should be over a larger area. And if it's a larger area, it's going to be cooler. And up here still, it's going to be cooler because it's still a larger area. But you look especially down here in the winter time, this is where you have your big extreme. You know, here you have now this huge area. So huge area. So it's going to be cold. And actually, really, with probably the reason that this is getting a little bit less is kind of we're getting around that curvature of the Earth, according to my thing here. So it's really not that much smaller than where we are between the two. Then, but you get down here, it's definitely going to be more and more and more as you go around that way. If we kick over to the other side, well, here, this one here, we're looking at it's winter for us. And the most intense sun rays are going to be right about here. Kind of right about that 23.5 degrees. So this is the most concentrated. So it's going to be the hottest. And as we move away, it gets a little bit cooler and cooler still. You get a little bit cooler, cooler still, and really cool. That over here you're seeing you have this huge area that sunlight spread out over. And really you can kind of look at it as though for these people here, you got your person standing right there. We'll make our purple person. That the sun is directly over that person's head. If you have a person that's standing here, that sun is, if this is the horizon, that sun is coming in low to the horizon. This person here, the sun is directly overhead. And an experiment that we were supposed to do in class is looking at, well, for winter time, you'll see this person here, the sun's close to the horizon. So winter and summer, how does the sun look for those two things for us? Well, if we have the ground, and summertime, you have that sunlight coming in pretty close to overhead. So a beam of sunlight now is going to hit, say, this much of the Earth's surface. So looking at like one individual little beam. So the energy, the heat is concentrated, something like that. In the winter time, if you go look out the windows, the sun is really low in the sky here at school. It kind of rises in the east, but stays really close to those houses that are south of school. So if we take that same size beam of sunlight and we project this thing down, well, when that hits the Earth, we'll see how I do it drawing parallel lines. When that thing there hits the Earth, now instead of it being this area, it's going to be kind of this oval area. So if you take that same amount of sunlight, and instead of it being in this nice little circle sort of shape here, instead you have this much bigger oval shape. So the sun more concentrated, it's going to be warmer. And that happens in the summer. So the sun is more spread out. Here in the winter, it's going to be cooler because you have less joules of energy per square inch or per square foot of your ground. So that's kind of the gist on summer and winter. In the winter, the sunlight is spread out over a larger area of the Earth. So then, looking at the top up here, it's cooler. And that's kind of reinforced by this drawing we have down here on the right. The sun's more spread out in the winter time, so it's cooler. In the summer, the sun's more directly overhead, so the sun is in a smaller concentration of the Earth's surface. Or you could look at the drawing over here. The sun is on a smaller area of the Earth's surface here, so then it's going to be warmer because the sun's more directly overhead.